Hi there, mg5004 DE5418. This is topic 5. We're working from chapter 9. We're looking at trig, and this is class 2. What we can do here is we're basing the work on trig identities from the previous class. And if you look up some of those in particular, if you look up y equals r sine x plus alpha, then we can rewrite that as r sine x cos alpha plus cos x sine alpha. And what we've got to do is we've just got to make the comparisons between the numbers. So what we've got to do here is we could also use this one. We could also use y equals r sine, theta minus r alpha. And we could have the same thing. We would have that y was equal to r sine theta cos alpha minus cos theta sine alpha. Again, it's just from a list of identities. Now, if we were asked to write it like this, then we would use that alpha is equal to tan inverse of b over a, which is negative 2 over 3, and it's going to be in quadrant 2. And r is going to be the square root of a squared plus b squared, which will be square root of 13 in this particular case. And then we can rewrite 2 cos theta plus 3 sine theta as now root 13 sine theta minus, now if we continue along here and we get our alpha, so alpha equals tan inverse of b over a, we're going to get that alpha is equal to 5.695. So what we've done is we have rewritten that in a particular format like that. We can also write it as the first one, y equals r sine theta plus omega. Now perhaps this time it might be easier to see what we're actually doing. Let's write the expansion out. That's a theta, and that's an alpha. Okay. R is equal to the square root of a squared plus b squared. Now, just making the comparison, forgetting about the r for the moment, we've got sine theta here. What's the number that's multiplied by sine theta? It must be 3. So cos alpha must be 3. And similarly, if we look for the number that is written by cos theta, we find that it's 2. So sine theta is equal to 2. Now, if we wanted to find tan alpha would be sine alpha over cos alpha, which would be 2 over 3. So alpha is tan inverse this time of 2 over 3. Now each expansion has a slightly different rule, and if you see what you're doing rather than just blindly going ahead, then you can make the comparisons each time, the correct comparisons each time. What we've got here is, and the way to remember it is that the number that's by the coefficient of cos theta is, the coefficient of cos theta is b. And a lot of students remember that by saying they remember it just b cos. A bit corny, but never mind. You remember that the number by the cos is b, and therefore the other number, so the number by the sine, I should say cos, is b. The number by the cos is b. The number by the sine is a. So if you remember that the number by the cos is b, the other number must be a. Number by the sine is a. So now we can get the rules that r is equal to the square root of a squared plus b squared, and in this particular case alpha equals tan inverse of, now we've worked it out, it's b over a. The usefulness of this is, suppose we wanted to solve something like that, where 2 cos theta plus 3 sine theta is equal to 2. Then we would have to rewrite it in some format, some different format, and then solve it. We'll do the second one on the page in class, but let's have a look at the first one. We've got y equals 2 sine x plus 3 cos x, and we're going to rewrite it in the format r sine x plus alpha. So we can work out what r is. R is the square root of 2 squared plus 3 squared, which is root 13. And by making the comparison of the expansion, if we expand the right hand side, then we can see that r cos alpha is equal to 2 and r sine alpha is equal to 3. So tan alpha is equal to 3 over 2. Because sine over cos. So that's in quadrant 1, and if we look that up on the calculator, we get 0.9. So if we were to draw that, we'd need to have the time period. The time period is 2 pi, and what we've got now is alpha. Alpha is our shift to the left. So we're going to shift the curve to the left. Haven't left myself much room. 2 pi, pi by 2, 3 pi by 2. And instead of having our curve here, we're going to move every point to the left. So by that much, that much, that much, that much, oops, that much, and that much. So our curve is like that. Now the question said find where that is equal to negative 3.5. Now we could do that on the graph, because this top point here is root 13 and the bottom point would be negative root 13, and what we're looking for is where negative 3.5 hits the graph. So it's going to be there that we're looking for, and there that we're looking for. Okay, we better do that algebraically. It's not going to be accurate enough to do it from there. So we've got as far as saying that root 13 sine x plus 0.9828 equals negative 3.5. Okay, bit of algebra, just divide both sides by root 13. And if we call z the bit in the bracket, so now we've got sine z equals negative 3.5 over root 13. Z equals sine inverse of negative 3.5 over root 13. So z is equal to two numbers. Just got another email. Z equals negative 1.328. I guess if I close my email in a minute, that won't happen. Or 4.4698. Now, z equals negative 1.328 is going to be out of range. So, just to repeat that, z is negative 1.3828. If we want it in the right quadrants to match the diagram, then z has to be 2 pi minus that, or 2 pi plus that. So 4.95495, or the 4.4698 as we had. Now that's z, so we need to find then that x, from up here, z minus 0.9828 will equal x. So x then is equal to 3.972 or 3.487 once I've gone down to 3dp. And if you look at the graph, those two numbers match what we've got. We can find the inverse trig identities. We do have to limit the y maybe or the x, because otherwise it won't be a function. You'd just get an infinite number of solutions. But what we've got here is that sine inverse of 0.4, say negative 0.4, is the angle such that sine y equals negative 0.4. So if we look at our curve, we can find that y must be negative 0.4-ish. Here we've limited y to being less than pi, and we've limited x as being between negative 1 and 1. So if we're looking up the inverse cos of 0.45, we'll find that it's 1 point something. Similarly, here we need to limit y to be between negative half pi and positive half pi. And if we were looking for an example to find inverse tan of negative 0.7, it's the angle such that tan of something is equal to negative 0.7. So if we need our tan to be negative 0.7, it's going to be down here somewhere, and our x, or gamma, whatever, is going to be equal to negative 0.6. So the situation that we're looking for is we've got x is going to be here. Now this is not true, this is just the background of what we've been doing, and it will lead us into topic 6 when we get there in a week. But it's just what we've been doing before, and there's nothing new. This is just ordinary trig that x equals the hypotenuse times cos, y equals the hypotenuse times sine of that angle theta. And you can prove this. Tan theta equals y over x, or tan theta equals sine theta over cos theta, which is y over r over x over r. So it gives us that tan theta is y over x, so theta equals inverse tan y over x. Now we're going to use a different way of plotting a curve. R equals 1 plus cos theta. Now you can put in values for you can put in values for theta, and you can work out r, which is all very well, but before then you can draw that on a graph, you actually need to find x and y. So we have to have some way of doing that, and it's all to do with the triangles like that. I will do the working of that in class, but what we will find is that the graph is a cardioid graph. Oops, like that, like a heart. You can use Desmos to check that if you want, but we'll prove it in the next class. We've done all these. We've done hyperbolic sine when we were looking at the exponential functions. We've done the definitions of sinh and cosh and tanch, and the list of identities is in the textbook. There's just a little rule that's called Osborne's rule, that if you take any circular function like ordinary sine or ordinary cos and replace any of ordinary sine by the corresponding hyperbolic one, and change the sign, as in the SIGN, of every product or every implied product of two signs, then you're going to get all the rules that we had before for sinh and cosh and tanch. You've seen those graphs before of the hyperbolic functions, and to find them you can use the calculator. I just use, I click the button, I've got an HYP button, and then I want to use sinh, I just click sinh, etc. These graphs we've all seen before, there's nothing new. And on the final slide for this unit, it's again some inverse hyperbolic functions which we did before, and just some alternative definitions of them. If you need them in the exam or the test, you will be given them.